We are going to look at ideal gas law. Some of this will be review, so it may be very familiar, which is a good sign. You may have seen a graph like this before where they are showing the relationship between volume and pressure, and it makes sense because if you take a balloon and you squeeze it, you're lowering the volume, you should see an increase in pressure, and that's essentially what this graph is showing you here. So if you reduce the amount of volume, you're going to increase the amount of pressure. Or if you are increasing the amount of volume, you should decrease the amount of pressure. Okay, now this is to explain why you have to convert any temperature to Kelvin. Please remember Celsius, you couldn't have negative numbers, and with gas laws, we cannot do calculations with negative numbers. Notice that at the very bottom left-hand corner here, the temperature is 0. That is absolute 0, and supposedly if we were able to lower the kinetic energy of a gas, we should eventually reach Kelvin, or 0 Kelvin, I should say. This has not happened. We've gotten very close to it. It is extremely challenging to try to limit the average kinetic energy of a gas. But theoretically, we should have 0 volume when we reach absolute temperature. So please, 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 whenever you do any kind of calculations, you want to make sure that temperature is in Kelvin. Now, notice that if you were to increase the amount of gas in a container, the slope of the line increases significantly. Now, the amazing thing that happens with gas laws is we assume it doesn't matter what kind of gas it is. It could be oxygen, it could be nitrogen, it could be helium, it could be argon. All we care about is the number of particles. We don't care about the type of gas, and that's why this kind of law works very well for us. Now, the same thing happens with Avogadro's principle. You are assuming it does not matter what type of gas it is. So we could have many different gases. All we care about is the amount. So notice that they all share the same volume, and as a result of it, you should see the same number of particles because they have the same volume. So you're assuming that we're talking about 0 Celsius, which is 273 Kelvin, and 1 atmospheric pressure. So we are saying that it doesn't matter what type of gas, they all share this property. Now, standard temperature and pressure, this is something that you should know when we're looking at gas laws. When we're talking about standard temperature and pressure, we're talking about 273 Kelvin or 1 atmosphere. Now, I don't know if you remember my cardboard box that I had in the classroom is essentially a box of air, and that box actually equals 22.4 liters. So long as the gas is at 273 Kelvin and 1 atmosphere, we're assuming that that gas will occupy 22.4 liters. You can also argue that it also will contain 1 mole of a gas. And we should know that when you're talking about 1 mole of a gas, we're talking about 6.022 times 10 to the 23rd particles. Okay, so I'm assuming that you will have access to your cheat sheet and you will have this equation on that cheat sheet. Please note that the R value, you have to be very careful about R values. If they give you torr or they give you millimeters mercury, you may have to convert that pressure to atmospheres. If they give you pascals, you want to make sure that you use the R value that is related to that unit. So R is very tuned into what the pressure unit is. The other thing is liters is part of the gas law calculation. So if they give you milliliters, you want to make sure that you convert that to liters. And then lastly, anytime you do a gas law calculation, please, please, please make sure that it's converted to Kelvin. So here's an example where they give you 8.5 liters or volume. They give you the pressure with 16.9 atmospheres, and they tell you the temperature is 25 C. And they want to know moles. So notice that you're going to be solving for the N value for this. The first thing you should automatically do is convert 25 to Kelvin. So notice that they changed the unit of Celsius to Kelvin, and they made it 298. And when you do the calculation, you get 5.9 moles of helium. And this should make sense. So please try to keep track of the values to see if your numbers make sense. The other thing is too, when you are doing calculations like this, you need to show your units. So don't leave numbers without any units, because you want to show that things cancel and that your overall unit is moles. Okay, so here's another example here where they give you 1.5 liters, which is volume. They give you the pressure, which is 0.99 atmospheres, and then the temperature is 32 Celsius. So they want to know how many balloons you can get with this amount of helium. So the first thing you want to do is you want to change your temperature to Kelvin, and then you're going to solve for volume. So notice they converted the temperature to Kelvin. They got 305, and they figured out the volume. Now you're not done, because you want to take the 1.5 liters and take your volume and divide by that to tell you the number of balloons. And when they do that, they find it to be 99 Luftballons. I'm thinking of the popular 80s song that I used to listen to. Okay, so here is another problem where they give you volume, 850 milliliters. Notice it's in milliliters, so you probably want to change it to liters. They give you pressure in atmospheres, and then they give you temperature. So once again, you want to change temperature to Kelvin. Now they give you mass of the gas, and notice they say that the evacuated vessel has a mass. So that is the mass of the container. And then they say the combined mass. So they're going to give you the mass of the gas by allowing for subtraction. So you're going to have the mass of the gas, but notice that with ideal gas law, there is no mass that's part of that. The thing that we don't have is moles of the gas. So we're going to figure out the molar mass of the gas using moles and using the mass that they give you. So initially you're going to solve for N, and then once you find N, which is moles, you're going to take the mass of the gas and then divide by the moles to give you molar mass. So once again, they converted the volume to liters, and they converted the temperature to Kelvin, and they got the moles of the gas. But they're not done, because they want molar mass. So they're going to subtract 142 minus 138.45, and that's going to give them the mass of the gas. And then they're going to divide it by the moles that they discovered from the previous problem. So there is the molar mass of that gas. Okay, so if you want, you can write this down. Notice that they're talking about mass over volume. Now, mass over volume is the same thing as density. So this symbol that they show you, rho, that is actually density. And what they do is they essentially substitute it in with mass and volume. And they're plugging it in using molar mass. So you could have a problem like this where they give you density and you need to figure out the molar mass. So notice that they give you the density, they give you pressure, and they give you temperature, and you would plug it into this formula at the bottom here to figure out the molar mass. Once again, make sure that you take temperature and convert it to Kelvin. So they went ahead and did that, and make sure too that your R value matches your pressure. They were working in atmospheres, so they used the R value with the correct units for pressure. And when they solved it, they got 80 grams per mole. Okay, so here is the combined gas law. Um, this is assuming that you're seeing a change in pressure, a change in temperature, and you're solving potentially for a change in volume. So for this kind of problem, you're going to see about 5 values, and one of them is going to be missing. So that's the only way that this can work. Here they have a gas. Notice they give you 2 different temperatures. They give you the initial pressure, but they don't give you the final pressure. So you are missing it. Now, the other caveat here is they're talking about constant volume. You could argue that this is Charles' law. I don't know if you remember Charles' law. I'm sorry, no, it wouldn't be Charles' law. It would be Gay-Lussac's law, because we have pressure and we have temperature. So they're using combined gas law, but they're assuming that one of the values doesn't change. So they get rid of volume and they essentially do pressure over temperature instead of PVT. And as a result of it, they got the new pressure. And please remember, this should make sense. So if you're increasing temperature, you should see a change in pressure that relates to that increase, especially if you're keeping volume the same. And then lastly, they show the fact that they wanted to convert it to millimeters mercury. So they use the relationship of 760 millimeters per 1 ATM. I would make sure that you have that somewhere in case you need it. Okay, Dalton's Law. So this is another one where it doesn't matter about the identity of the gas. It just matters that the sum of the individual pressures equal the total pressure. So notice they say that P total equals P1 plus P2 plus P3. So you have multiple gases that are occupying the same container. As you keep adding more gases, the total pressure should increase. So here they say that we have 2 different gases. One is oxygen, one is nitrogen, and they're put into a 6-liter tank that's kept at 20 Celsius. Because they give you mass, you probably want to convert that to moles, because it's not going to work if you just keep it in grams. And I don't know if you remember from Dalton's, we have to figure out the partial pressures of each. So first you want to do is convert that mass to moles, and then you want to plug it into the ideal gas law to solve for the individual pressures. So they did this here, where they converted the mass to moles. They plugged the moles in with the ideal gas law constant, temperature, and volume, and they got the individual pressure for nitrogen. Then you're going to do the same thing with oxygen. So notice with oxygen, once again, they converted the mass to moles, and then they're going to plug it into the ideal gas law. So there's the ideal gas law, and they're essentially solving for the individual pressure of oxygen. Then for total, you just add them. So that's the nice piece, is it's pretty straightforward. You just need to remember that you want to combine those pressures to get the total pressure. Okay, mole fraction. I don't know if you remember mole fraction with Dalton's law. So you're looking at the number of moles of each gas, and notice that the denominator is the sum of all the individual moles. So in order for this to work, this ratio, you need to have the individual moles of the gas, and then you need to have the total moles of the mixture. So if they gave you just the individual moles, the good news is all you would have to do is add them all up, and that would become the denominator. And then the individual numerators would have the separate moles of each. So here is the mole fraction of helium. So they took the individual moles, which is 760, and they put that in the numerator. And then the denominator is essentially all 3 moles added together. And please remember, if you want a shortcut, you can do the mole fraction of 2 out of the 3. And because the total should equal 1, you could subtract the 2 added together. And then their difference should give you the third mole fraction. So all 3 together should equal 1. So if you took the 0.62 and the 0.231 and you added them together and then subtracted from 1, you should get 1.148. And I'm assuming the AP reader would understand that you knew that. Just make sure that you show that calculation. So here they're showing you that if you wanted to solve for the unknown third mole fraction, because the total should be 1, you just have to take the 2 and subtract them from 1, and that gives you the remaining fraction. Okay, now I've seen this on free response sections where they give you a mole fraction, they give you the total, and you have to figure out the individual pressure. So notice that the mole fraction is part of the calculation. So if you have the total pressure, you multiply the mole fraction by that total pressure, and that should give you the individual pressure of that gas. So they took the mole fraction, and mole fraction, please remember, that has no units. That is a pure number. So it's just a ratio that explains the amount that would be part of the total pressure. Okay, I don't know if you remember doing this in the lab, but there have been instances where you've had to collect a gas over water. It's easy to trap gases because obviously they float to the surface. And I don't know if you've ever experienced this at like a pool or a lake where you have a container inverted and it traps the air when it's submerged underwater. We do something similar with chemistry. So here is H2O2, and I don't know if you remember, this is hydrogen peroxide. They're combining it with sodium hypochlorite, and they produce salt. Salt is dissolved in water, so you don't have a solid. We have pure water that's part of that, and then we have oxygen gas. And notice that in this second graduated cylinder, you see the bubbling up of oxygen that's being collected. Now, the challenge with this is that unfortunately some of the water has vapor pressure, and that mixes with the oxygen. So we have to take that into account when we're doing the partial pressure of oxygen. So typically what you do in this situation is you have to line up the water level inside and outside of the graduated cylinder. And what that does is it makes the gas that is trapped in that container equal to the atmospheric pressure. Now notice that the P total is a combination of the oxygen gas pressure plus the water pressure. And the nice thing is we can go to a table, and the table is based on temperature. So we are going to subtract the pressure of the water at that specific temperature. So in order for this to work, they have to give you the vapor pressure of the water at that specific temperature. So when you solve for the total pressure, you're going to subtract this value from that total pressure to give you the pressure of the individual gas. So in this problem here, they give you mass. They say it's an unknown, so we don't know what the mass of it is. They give us temperature, they give us pressure, and then they give us volume. So we're going to solve for moles first, and then we're going to then figure out with the pressure, we're going to use the pressure first, and subtract um, the water vapor pressure, because we don't want to factor that in with the moles of the gas. So here we go. So the first step is to convert it to atmospheres, which they did here. We're going to find the partial pressure. So we have to subtract the water pressure that they gave us, because if we don't, we're going to get the wrong answer. So they did that, and they found the atmospheric pressure for that individual gas. Now we can solve for the moles of the gas. So here we're going to set it up. We have the unknown pressure, we have the volume, we have the temperature, and obviously gas law constant. So that is the moles of the gas. And then molar mass is pretty easy. We have the mass of the gas in grams, and we would just take grams divided by moles to give us the molar mass. Okay, and depending on what it is, sometimes they give you clues to what the possible suspects are for molar mass. You could match, if it's a noble gas, you could match that with the periodic table to identify the gas. But in this situation, they're not asking you to identify the gas.